after we have seen in the concept of hard and soft margin support vector classifier in the previous video clips, in today's lecture we will introduce the concept of using nonlinear classifier and the concept of kernel function in SVM. The contents in this lecture in the handout are taken partly from this textbook, the elements of statistical learning, and also the introduction to statistical learning ISLR textbook. And there's a great resource, both the online, the videos, the lectures, and the note in this link. So this is a very useful materials for this subject. What we have seen so far from the linear classifier using the linear hyperplane to classify data from two classes may not work well if we take a look at this example. The pink and the blue classes are now laid out in the space in this way. Okay, so maybe if you see the labels and everything here, you may see that, okay, maybe you should classify it using these two decision regions. But then if you attempt to use the linear classifier as we see, it turns out to have the result like this, and there's a lot of error here. Okay. So one way to add nonlinearity, to add like more complexity to your classifier is to think about how can we extend from linear function to nonlinear function. So one thing you could do is that you map your original feature using the nonlinear function, like the square function, or you can use some nonlinear mapping h1, h2, and hm. Okay. So your x in the original space has n dimension, but when you use the nonlinear mapping hm, so this m can be chosen, and this n can be larger than the original dimension. So basically you can use nonlinear mapping to an enlarged space. Let's recap again how the classifier is computed. You see that let's bring out this notation. This is the the notation of an inner product between x and z, and when x and z are Euclidean vectors, it's basically x transpose z. In KKT conditions of the dual, in the SVC formulation, it turns out that at optimum, your W is the weighted sum alpha I yi xi. Okay, alpha I is the Lagrange multiplier. Xi and yi are data point. The sum are taken overall data observations, but you know that in the KKT condition, your alpha I is between 0 and c, which means the sum in order so for those alpha I that is strictly greater than 0, for those xi, for those data point, for those only those support vectors will have contribution in order to construct your W. Okay, so when we plug in this W in your classifier function, so you just plug it in, okay, and you see from this expression that this is scalar, this is scalar. Only xi is a vector, so your x transpose will be multiplied with this xi. But then you can use just use the concept of inner product, right? So it turns out that only the amount of the inner product is in the sum is in the sum of this in order to compute fx. Okay. So the summation here requires much fewer terms. You don't need all the n observation. Only those I that correspond to positive alpha I. Okay. So when we see the expression that, okay, when you compute a linear classifier, only the inner product is required. Now we can generalize this concept. How can we think of this inner product in a more general way? And that's the idea of the kernel functions. A kernel function is a function of two arguments. So a pair of x and c are from the product space Rn and Rn, and it returns the value. It returns a scalar value. The kernel function will have certain properties. So to formulate the problem, we give you the problem setting. An SVM, the SVM is an extension of SVC, support vector classifier, using the feature space, using the feature that are mapped using the nonlinear function. Okay, you have H1, H2, and HP. So this is P dimension. Your final prediction, your classifier function will be nonlinear in X, okay, with this H, and HX transpose W plus B. Okay, the dimension of the enlarged space, which is P here, is allowed to get very large. So if you follow the same step of how to derive the dual problem and all of that, we give you the final result first. It turns out that your W, this parameter of the SVM, will be expressed as the linear combination of alpha I, yi, h of xi. Okay, this is a function of data, the training data. Okay, so when you compute the classifier at a new test point, HX transpose W. Okay, I'm gonna plug this in. I hope it's not hard. It's not hard at all. Okay. All right. You will see that it will require only the inner product of HX transpose and H of xi. So very similar to the previous one when we compute in the vector case, in the linear case. Okay. In order to compute fx, we only need the inner product between hx and hxi. We don't need to calculate h of x explicitly. The primal and the dual nonlinear SVM are the following optimization problems. Okay, so everything it just looks. It has the same meaning interpretation. You only replace the linear function of in x by the nonlinear function. So I'm gonna highlight the term that is replaced by the nonlinear mapping. Okay, so it still have the primal SVM is to what? I want the margin to be maximized, and I want to also to minimize the slack variable. With this objective, I focus on classifying the training data correctly. Okay, I have parameter C to trade off between these two guys, the margin and the slack variables. Okay, we follow the same dual. Same derivation steps. Okay, we will end up with similar KKT conditions. Let me just point out here. This is the KKT condition for SVC, but for nonlinear SVM, the term that is originally linear in X is now replaced with nonlinear in X. The term W, this is the weighted sum of yi xi, and now it will be replaced by h of xi. This also, the complementary slackness will be replaced by nonlinear function in xi. Okay. Where are we? And the if we take a look at the dual problem, the only term that is changed now is originally in the dual SVC, this is the inner product between xi and xj. Now, for nonlinear, you have the kernel function. Okay, everything else stays the same. So, for example, you have constraint that is linear in alpha I. You also have box constraint in alpha I. Okay. So one important note is that when you take a look at the primal SVM, now your variable, your optimization variable, sorry, I missed the Z, W, B, and Z, co-subjective, quadratic in W, linear in Z, the constraint, linear inequality constraints are linear in W, B, and Z. They are linear in optimization variable. So this is a quadratic program. Okay. Take a look at the dual. The dual is still a quadratic program. Okay. So this is quadratic function in alpha I. This is linear equation in alpha I, linear constraint, linear inequality constraint in alpha I. Okay. In the dual, you don't actually need to compute the value of hx. You don't need that explicit knowledge of nonlinear mapping. Only the information of the kernel function, which is inner product between nonlinear functions values, are required. This is the important note. Let's take a look at the kernel function properties. The SVM has the form, after you plug in the expression of W, you will see fx is a linear combination of alpha I. Your x is the test point. Your x here is some test point, and these xi are the training data you use to train. Okay. So and as we point out earlier, these sum only take place for those alpha I that are non-zero. So when so from the definition of the kernel function, that is the motivated from this derivation, is the inner product between hx and hz, right? So as you know that the inner product has to be symmetric, so the kernel function also need to be symmetric, which means if you just swap these two input argument, all right, that should be it should give you the same value. Also, for inner product property has the property that when you take the inner product between x and itself, it's going to be non-negative, right? So the kernel function also need to satisfy that non-negative non-negativity. There are four common kernel functions in application. The first one is a linear one, right? It will, if you pick this choice of the kernel function, it just goes back. It goes back to SVC, the linear classifier. Okay. The inner product also give you very similar meaning with the correlation value, right? The second example is the polynomial kernel. There's some parameter gamma, r, and d. D is a positive integer. Gamma and r are some positive numbers. For example, when x and z is in R2, right? The polynomial one would be like 2 x1 z1 plus x2 z2 plus 3 when d is 4. Okay, so you see that this is a nonlinear function in the two arguments. The third example is the most popular one, the radius basis function. It takes the form of the Gaussian curve, where gamma is the decay rate. Okay, so on the x-axis, this is the distance between x and this is the distance between x and z. So gamma looks like it gives you how fast does it decay, all right? It's like the inverse of the variance in the Gaussian density function. The next one is the hyperbolic tangent. With this argument, you get to choose gamma and r. Okay, now we have some illustrative plots for polynomial using different values of gamma. Okay, for RBF, I hope you can recognize and you can specify which one matches with 1, which one matches with gamma equals 5. So when gamma is large, the RBF should decay faster, right? So when gamma is large, it should be the red plot. Also, the hyperbolic tangent. Hyperbolic tangent is e to the x minus e to the minus x, e to the x plus e to the minus x, okay? So the x-axis is the inner product of x and z, okay? So when gamma is large, that should correspond to the faster decay, hyperbolic tangent. So for RBF, we have some observations that the kernel function x star and xi, okay. So it takes the form of e to the minus gamma x star minus xi, right? So when x where should I plot? Okay, so this is the Gaussian, right? This is the distance between xi and x star. If the distance between these two guys are very far, suppose the distance is here, the value of the kernel function would be small, So observations, so the training data point that is far from x star, the test point, will have a small role in the predicted label for x star. Okay, let's take a look here again. Okay, this is to confirm again. Your final prediction about a test point x depends on the kernel value function. So if xi is far away from the test point, is very far from the test point, if the distance is far, right? Looking at the behavior of the kernel function, if the distance is far, the kernel value will be small. If this value is small, those xi whose kernel function is small will have a little role, will have insignificant role in the prediction outcome. Okay, that's one thing. So RBF, so one simple message, RBF has a local behavior. Only the training data point that is close to the test point will have more significant contribution. Here we have some numerical example. The figures are taken from ISLR textbook and ESL textbook. On the left column, this is when you use the polynomial kernel. On the right column, this is using RBF. You have the pink and the blue class, okay, and the solid line. The solid line is the decision rule given by the expression of your fx, okay. So when fx greater than some threshold, you get one side of the decision region, all right, and on the other side. So it seemed to work pretty well for polynomial. So you have two decision lines here, because I believe in the book that it's maybe cubic or quadratic, so I'm not sure. Okay, so the dashed line is supposed to be the margin. Okay, it's supposed to be in the margin. For RBF, I mean, from this plot, it seems to work pretty well because it's classified the blue and the pink class correctly, quite correctly. So for RBF, even though the decision rules is different form, okay, from the polynomial, it still works well in this case. We have another example, another experiment where you also compare between polynomial and the RBF. In this case, the ground truth data are generated from mixture Gaussian. The blue one, the blue line here are decision rule obtained from the optimal classifier, which is the optimal base. The solid line is the decision rule given by the polynomial kernel function, and of course the dashed line are the corresponding margin. So there's a certain value of error. This is in training 0.18. Okay, on the right hand side, what you get is different decision region by RBF kernel function. Okay, and if you compare between these two figures, you compare the trend. Okay, in the training result, RBF is better. In the test, this is where you should look at the test results. The test error of the RBF is lower, which is better. And of course, in both methods, the error must be higher than the optimal base because this is optimum. You can also see that the region obtained from the solid one seem to be close in a certain degree to the base decision region. To test the performance of a classifier, this is another way to look. If we look at the overall performance using the ROC curves, this is to illustrate on the hard data where we have patients and we want to classify whether a patient has a heart disease or not. Predictors are age, gender, and cholesterol level. So it's a binary classification problem. And what the classification indicator is to use the graph of ROC. ROC curve, if you review, this is the curve between TPR, true positive rate, and false positive rate. So for each classifier, you get the form of fx, the classifier, and you're gonna you get to pick a value of a threshold t. So you classify these data point to a patient who has heart disease if it's greater than t, for example. And for that outcome, for that prediction, you're gonna maybe you predict it correctly or incorrectly. All right, so when you evaluate these on bunch of test points, you can count the false positive rate and true positive rate. So for one value of t, that corresponds to a certain value of TPR and FPR. As you vary t, all right? Remember that when t is lower, you classify to a disease case more easily. Okay, so as you vary t, that is when you get the whole ROC curve. Ideally, an ideal classifier is the one whose ROC curve lays on the northwest corner, because that means you have both true positive rate and low false positive rate. At least your classifier should be better than the diagonal line, because these correspond to a random guess classifier, the one that predict the outcome as positive and negative with 50% chance. The left figure is the comparison between SVC and LDA. Both of them are linear classifier. So I would say they perform quite comparably well. On the right hand side, this is SVM. Okay, is SVM as you play with the value of gamma. Gamma is the decay rate of RBF kernel function. As you increase gamma, it seems that as you increase gamma, the ROC curve is improved. Okay, remember that when gamma is increased, your model will if gamma is large, so only those training point that is close to the test point will have a role. So when gamma is large, your SVM becomes more becomes to have more local property. So your model is more nonlinear when gamma is big. Okay. These results it seems that the orange one is the SVC, the linear one. Okay, so in this result you see maybe the value of gamma has to be chosen wisely. Now we also need to to take a look at the result from the test data. This is train, this is test. Okay. As you can see, for the first case, the ROC curve in the test case seems to be slightly worse. So it bends lower to this direction, which means it's worse, right? Worse than the train results. In this case, both of them are still comparably, like they're quite perform with the same degree. Okay, so maybe SVC is slightly better in these operating points. But now if you take a look at the SVM in the train result, big gamma is the best, but the test result, the big gamma now seem to be the worst. while the SVC, the linear classifier, is still better than the nonlinear SVM, where gamma is big. So to make a fair judgment about a classifier, first of all, you need to look at the test results. And this experiment just shows that the parameter of your kernel functions, gamma here, need to be adjusted, need to be tuned. And we can do this using the cross-validation. So in order to sum up, in order for you to tune this parameter correctly, let me sum up the property of these parameters. In SVM, nonlinear SVM, you have C and gamma. C is a penalty parameter that appears in what? Appear in the cost objective. Right? Remember that this Z is a slack variable. It's a slack variable when you allow your method to misclassify some point to be on the wrong side of its class. So when you have high C, if you choose high C, you care more about this term, you penalize more about this. So you focus more on classifying all the training points correctly. So in this case, your model is going to be more complex. All right, your decision region will be more weakly. Okay, and for low C, of course, the effect is on the other hand, you care less. All right, you allow some point to be on the wrong side, so the decision surface is going to be smoother. Gamma is a decay rate for the RBF kernel function. So if we again, if we plot the kernel function here in two cases, okay, in two cases mean when you have small gamma and large gamma. Okay, your final prediction would be the sum of alpha I, y I, k of x I x. Okay. So the influence of the influence of your training observation in the final prediction outcome will depend on the kernel value, kernel function value. So let's say the same influence is of course the same value of kernel function. So we make a comparison between two cases, large and small gamma. All right, in order to have the same k, for small gamma, the distance would be, for small gamma, in order to have the product to be the same k, the distance will be large. All right, so for small gamma, small gamma should be the mint color, right? In order to have the same k, the same horizontal line, right? So you can reach a far training point that will allow you to have the same effect on the model. On the other hand, if gamma is large, this distance will be small, right? This distance will be small. For the same k, when gamma is large, the distance would be small. So only a closed single training point can reach, only a closed single training point will have the same contribution to the final prediction outcome. Okay, those two parameters can be chosen via the cross validation. Now let's see some example. This figure is again taken from scikit-learn. Okay, now we have gamma is small and gamma is large. So you increase gamma in this direction. Okay. If you just take a look at the experiment, I mean, of course, if we just kind of if we forget about the principle, maybe just for a second, if you look at the results, look at the evidence, okay, you have blue and the red classes. So in this graph, it seems that the decision regions seem to be like linear, right? Seem to be simple. As you increase gamma, you have, so the decision region seems to be more complex. It tends to capture more nonlinearity in the data. All right, and go back to go back to our previous conclusion. Okay, for higher value of gamma, only a closed single training point can reach. Only a closed single training point will have the effect on the outcome. That's why it tries to capture a lot more local property. Okay. Now, if we focus, so you have to balance, right? Using small and big value of gamma tends to be linear. It could be more nonlinear and very nonlinear. If we take a look at an intermediate value of gamma, what about we take a look at this direction? You have C, you increase C in this direction. Okay, in this direction. If you just look at the graph, what happens? So here it seems to be that the decision region is nonlinear, but it seems to be smooth, and it is getting more complex as you increase C, right? If you look at the graph, and that agrees with our interpretation. When you have high C, you focus more on classifying the training points more correctly. Okay, so in conclusion, you're gonna make a grid. You're gonna select a a set of values of both parameters C and gamma, and then you use cross validation. In this one, okay. In this one, you select a value of gamma 0.1, 0.5, 1, and 5. Okay. For each value of gamma, you discretize the value of C. Okay. You use validation data, like the one that is not the training data set, and you compute cross-validation error. Okay. So that's the cross-validation error. The error for classification, the error is just the complement of the accuracy, right? So of course, for gamma equal 5, the optimal C that you should pick is the one correspond to the smallest test error. As gamma decreases, it seems that the optimal C is getting bigger and bigger. And why is that? Because here in this graph, gamma is decreasing, right? Gamma decreases, so your model is less nonlinear. The decision region is smoother. Your model is less nonlinear, less complex. But in this direction, in the x-axis, the C increases. When C increases, the model is more nonlinear. All right. So this is a conclusion. I mean, that's a good compromise, optimal compromise for a pair of gamma and C, and you can choose it using the cross-validation error. From these cross-validation steps, it seems that you have to compute multiple times, right? How many values of gamma you pick, how many discrete value of C you pick. So it seems that you have to solve SVM multiple times. So in terms of algorithm, there's a path algorithm for you to compute the weight W for many values of C. The detail is in the textbook. So here's the conclusion. In this video clip, the message you should get from the lecture is the effect, the property of two important parameters of SVM, penalty parameter C and the decay rate of the Gaussian or the RBF kernel function.